So hello, everyone. I'm Wei Jiaxu. So welcome to the bi-weekly Lighting Talk series on smart city research. And this talk series is funded through the UT School System Project. So every other Friday, we invite speakers from UT, industry, and government to share research and events and the needs related to the smart cities. So if you're interested in this topic, please feel free to visit our website for the past talks and other activities at smartcity.tech.utexas.edu. So for today, we are excited to have a Professor Christian Claudel, who is an Associate Professor of Civil Architectural and Environmental Engineering at UT Austin. He received his PhD degrees in electrical engineering from UC Berkeley in 2010, and his work at UC Berkeley is on the Mobile Millennium Traffic Monitoring System, which won him the Leon Croix Award from the UC Berkeley's. So for his talk today is about challenge and methods on data assimilation for flood real-time estimations. So without further ado, I will pass the mic to you. Please go ahead.
All right, so let me share my screen. I believe sharing is, I think sharing is disabled for now. Okay.
Can you try it again?
Okay, let me try it. Oh yeah, it's working now. All right. So, okay. So, all right. I guess can you all see my screen?
Okay. Yes.
Awesome. Perfect. So, good morning, everyone. So it's my great pleasure to give a talk today. My talk today will be on data assimilation for real-time flash flood predictions, the challenges and the methods. This is a joint work with my PhD student, Kun Kian, who is finishing his PhD. So my objective in today's presentation is to discuss the prime of sensing floods, as well as the prime of mapping floods with sensors. So floods, as you know, are a critical prime because it comes from the fact that most people now live in cities. So more than 50% of the population live in cities since 2008. And actually, we have lots of difficulties operating cities because we have a more and more concentration of people in the same location. So we are more and more vulnerable to climatic events, for example. In particular, we have distribution networks that are transportation, the power grid, the water grid. So we have to balance all that and to manage the disruptions that happen during specific events. We have to also respond to disasters, and when you have lots of concentration of populations, it's very difficult. We have also to have some resilience, and we are in the middle of a pandemic, of course, so we all know what this word means. But in particular, when we have some extreme weather events, and we have seen that in February, we have to find a way to minimize damage and to maximize the ability for people to restart their lives normally. So the motivation is floods. Why? Because floods are one of the biggest issues in the US and worldwide. If you look at casualties from natural disasters, most of the casualties come from floods, in fact. So it doesn't look very impressive, but compared to tornadoes, for example, or compared to storms, winter storms, but in fact, floods are very deadly. And the real prime of floods is that most of the people that die during floods are people that die trapped in their cars, so in vehicles. That's the main cause of death, and the root cause of these casualties is the fact that we don't have real-time accurate information on flooding. So of course, whenever you have a lot of rain, you get some information in the form of, for example, of weather alerts on your phone, but these informations are very imprecise and vague. Most of the time, you have a flooding alert, but actually no flood occurs. So it's very difficult to have some very precise information that would lead you to make a critical decision with full information. So the objective that we have is to try to sense floods. So how can we sense floods? And what are the possibilities of sensing floods, and then what are the challenges associated with the inverse estimation, so going from the sensor measurements to the flood maps. In a sense, that's the concept of data assimilation. What are the challenges for that? So the first problem is to sense floods. So sensing floods is something that is difficult because we don't have usually the equipment to sense floods. So for example, we can use wireless sensor networks to sense floods, but the problem is that it's pretty expensive to design sensors that are just meant to sense floods. Floods can occur or not occur. There is a low probability that a flood will occur over the lifetime of the sensor. So the cost-benefit ratio of flood sensors themselves is not great. So what we need to do is to essentially try to design sensors that are useful for multiple applications. For example, surveillance cameras that can also monitor water levels, or traffic sensors like the illustration here. This is some work that I've done previously on designing flood sensors that could also that were also traffic flow sensors. So traffic flow sensors with flood capabilities, and traffic sensors can have an interest, but if you have this added value, then that's almost a zero marginal cost. So that makes it more attractive as a solution. Mobile sensors would be very interesting, but currently they are not feasible, and we're going to discuss also why. So for the mobile aspect of sensing, floods are distributed events. So installing a fixed infrastructure can be costly. However, this can change because the cost of electronics goes down. I mean, tended to go down recently. So it could be that we could have a very inexpensive flood sensors that we could install in cities. But the key objective would be to first use mobile sensing, because mobile sensing, you can redeploy it at other locations. You don't have to have a permanent fixed cost plus the maintenance of that permanent system. The problem of mobile sensing is that if you use the currently available technology, you cannot really solve this problem of mobile sensing, because, for example, satellites would be the obvious choice. Satellite reconnaissance weather. Weather reconnaissance satellites are satellites that have capabilities to take pictures, for example, or to take images with synthetic aperture radars. However, the pictures cannot help while the flood happens, because of course you have a cloud layer, so you cannot see anything through the cloud. The radars can go through the cloud layer. However, they don't have the accuracy in altitude estimation to give you an assessment of the flood location and the path of the flood. Furthermore, these synthetic aperture radars, they are all low Earth orbit satellites, which means that they don't go. You cannot have a permanent coverage of every point on the Earth. It depends on whether a precise satellite is above a precise location at a precise time. So instead of using that, we can use, as I said, fixed sensors or mobile sensors. So here I'm going to go with fixed sensors very briefly, the work that we have done. So we have used PIRs, passive infrared arrays, plus ultrasonic rangefinders to detect the presence of water. It's a little bit involved. It's not just measuring the distance with a rangefinder, because you need to correct for temperature patterns in the lower layer of atmosphere. So close to the ground, you have huge gradients of temperature, and we know that the speed of sound depends on temperature, of course. So you have to definitely estimate and correct this effect to get a precise height measurement. So we have done this work in the past, and we have managed to get a good accuracy, both for detecting traffic. And so here you can see that these spikes correspond to cars that go under the sensor, as well as, so this is for traffic performance, but as well as flood. So here, if you look at the raw measurements, they are not very accurate, as I said, because the distance measurements are affected by the temperature, and that varies over time, and it's quite complex, the gradients in the atmosphere layer. But if you use machine learning, you can actually correct all these effects and get an accuracy of plus or minus 1 centimeter approximately. So it gives you a good precision. So these sensors are not installed in Austin. I just saw the question. They have been developed back in the day. So I had a startup company. I have a startup company with my former students that work on this, and we have some installed in Texas, but not in Austin. So to measure floods. So the other thing that I will discuss.
detail code, and it is regarding the grid info.
Sorry, can you repeat your question again? Oh, sorry. Okay. So if there is no, I'm not sure if there is a question. Okay, so we can answer the questions at the end. I guess that's probably going to be easiest. So now, if you look at so these are the sensors, and that come from Salim company that developed these sensors. So we have installed these sensors in a few locations, and we have in fact measured a few flood events, particularly in the Middle East or in flood-prone areas. The interest of this system is that you can really detect very well how flood propagates in cities. So, for example, we detected a flood in, I believe, I forgot which location it was. It was a city in Saudi Arabia, and that flood was interesting because it shouldn't have happened. It was because a drain was clogged that the water back propagated, and we could follow that and track that with the sensors. So it was an interesting application of this technology, which I believe is the only currently doable technology. In a few years, things might be different, but currently, I think the best way is to still use fixed sensor networks. For mobile sensor networks, we are working on this topic, and the objective would be to use things that can move fast to deploy sensors at different locations and estimate water levels. So the difficulty is that when you look at floods, there are situations in which floods are caused by rivers. So if floods are caused by rivers, you can use the same technology as what I showed previously. You just need some water level measurements. For example, a radar or an ultrasonic sensor are good enough to estimate the water levels above rivers. However, if you look at situations, for example, if you look at cities that are like this example that I showed, so it's the city of Jeddah in Saudi Arabia. So in that city, you have no river whatsoever, so you cannot install sensors. I mean, you have lots of possible locations where the flood could come from. You have an entire watershed that is hundreds of or thousands of square kilometers, and you cannot obviously install fixed sensors everywhere. It's a sad thing because there have been floods in these locations. For example, there was a flood in this particular city in 2009 that created 200 casualties, or more than 200 casualties actually. And these casualties could perfectly have been avoided because they occurred in the city, and the flood took place far away from the city initially. So it was really a few tens of kilometers away. So by the time that the flood hit the city, as a surprise for everyone inside the city, it could have been detected and tracked for a long time. So everything could have been avoided with proper sensing. And the idea that we have is that, of course, if you have large areas to monitor, you have to use drones, possibly fixed-wing drones, because the quadcopters don't have the right autonomy. And the system that we would like to try is a system in which you have drones that can do some measurements of the flood level. So you cannot use the classical cameras on drones, because when you have a flood, you have terrible rains, obviously, and so you have a very poor visibility. You cannot use synthetic aperture radars as well, because they are too inaccurate to go through the layer. Plus, they would require you to have a perfect estimation of the height of the drone above the ground, but it's not nearly accurate enough. So what we envision is instead to use some very tiny throwable sensors that could be dropped and that would flow with the water. And based on this flow, we could estimate if we have a flood or not. So these are the sensors that we have developed a few years ago that were based on printed circuits on paper. These sensors, I mean, they are not really sensors; they are just pingers, in fact, and they just ping a unique ID. And what we do is we just track their location using, for example, angle of direction, angle of arrival, or a time of arrival. If you can ping them back and forth, you can measure their position, or you can simply detect their location under a drone. That would probably be good enough if you have a short range of detection. Just the detection would tell you if you have an ensemble movement or not as your drone is moving above. So we have tested that on on one of the UAVs that was in use there from Caxt there. And so that's definitely doable with other fixed-wing UAVs. That goes without saying that the problem is that we don't have the right technology to do this right now. So even though the concept could theoretically work, there are some specific issues. So the first issue is how to develop the path planning algorithms for the UAV, because what you want is you have a limited number of UAVs, you have a very large area to monitor. So if you look at this map, it's gigantic. It's tens of kilometers, thousands of kilometers square. So if you have a limited number of UAVs, where should you put them to maximize the information? Because you want to have the highest amount of information in the fastest possible way. Given that floods are very extreme and fast events, you don't want to have the picture of what happened 2 hours after the fact. You want to have them right now. So how do you develop these path planning algorithms? How do you develop the inverse modeling algorithms to estimate the state of the system, which is a flood propagation, as well as estimating also the model parameters for forecasting the floods with in a more accurate way in real time? So you have to do these two things in real time: estimate the state, estimate the parameters, and then use that to predict with a better accuracy what happens in the next 5, 10, 20 minutes. And finally, also develop some control algorithms for UAV flight in turbulent conditions. So this is really something that is far away from state of the art. When you look at UAVs right now, they are totally incapable of flying in bad weather conditions. So this is some work that we have done with my former PhD student, Ofer Eldad, with a fixed-wing UAV that is here, this Major UAV. And the objective of our work was to develop an algorithm that predicts in real time as a function of the state of the UAV. So this, you can see here the state of the UAV as this on the left of this video. So this is the state estimated from the measurements that are on the right of the video. We use an uncentered Kalman filter to estimate the state. But once we have the state, our objective is to know what is the possible sequences of inputs that can be given to the UAV. So here we are not controlling the UAV, but we are just trying to determine the envelope of possible future inputs that the UAV can take, so that the UAV doesn't stall, doesn't overstress its wings, for example, or doesn't crash into the ground. So let me see. There is a. Okay. So here, the objective of this is to determine the safety. So this safety input sequence space. So we cannot easily find. So it's a 9-dimensional vector space, because we look, for example, here at the sequence of the next 3 or the next 5 inputs. Given that you have 4 inputs per UAV, that makes a 20-dimensional vector space, and you have to characterize what is the subset of that vector space that correspond to the safe envelope. So to minimize the amount of parameters, we chose an hyperellipsoid representation of that set. That's why we have ellipses when we do we cut it across a subspace. But from there, we use machine learning to determine what would be to train the learning of that safety envelope. As an hyperellipsoid, so the parameters, and then we have a mapping that connects these inputs that correspond to the states of the UAV to the parameters of this hyperellipsoid. We then perform cuts in this vector space, for example, to take the first input, and we just project the input that is given by the UAV to that on the surface of that ellipsoid. So that we project it so that it is inside that ellipsoid. So if it's outside, we project it on the surface. So you can see here in that example, we fly the UAV, which is this very tiny dot in the center of the video, and we try to stall the UAV. So for that, the user gives a very strong nose up input, which you can see as, so the nose up input is represented by the blue point. The blue point is the input, and the red points correspond to the actual position on the actuators. So we try to do a nose up input that is large, but the actuators is projected. So the actuators, the actual position of the elevators is maintained to be right on the ellipsoid. sorry, so let me go back to the view. So it's maintained to be right on the ellipsoid in such a way that the UAV doesn't stall. So even if we try to go away, we are projected again on the ellipsoid. And therefore the UAV doesn't stall. But that's, of course, that was manually piloted. If you had an autopilot, you would have also the same thing. So the autopilot would try to do things, but it would just be limited to perform within that safety envelope. So with that, we hope that it could be safe enough to fly over populated areas. Right now, it's still far away from being the case, but we hope that this could be achieved at some point. So next, data assimilation. So the data assimilation is the process of going from the measurements that we get from our sensors or from the UAVs to flood maps. So in data assimilation, we combine measurements with dynamical models, and the dynamical model here is the flood propagation model. So how the flood propagates. We use the measurements at different locations, and together with the sequence, so the sequence of measurements plus the flood propagation model will give us the possible states that we can have, so the possible flood maps that are compatible with the measurements and the flood propagation models. So of course it's a complex task because we have to use a complex nonlinear dynamical model, so the flood propagation model, which is encoded by a partial differential equation, and we have to estimate the state in the end. So the process is very simple. In the end, you have standard algorithms to do that, like the ensemble Kalman filter. So in the ensemble Kalman filter, you have a bunch of possible ensembles that each represent the possible flood map that could occur. And you have some forecasts. So the forecasts are the prediction of the model over the next time steps. You compare this forecast with the actual observations, and you apply the classical Kalman filter update equations to determine what will be the next possible estimate of the state. And when you run that process, you are actually assimilating the data with the model. So you're effectively combining the measurements with the model to get realistic flood maps that are compatible with the model and the measurements at the same time. So the ensembles here, these are an example of a cut of in the situation. So we have 16 ensembles here. So each of these ensembles correspond to a particular flood map. We propagate these ensembles, so each of them using the simulation model. We compare each of the outcomes with the measurements, and then we select ultimately, that's what the Kalman filter does, it will ultimately take the ensembles that have the highest compatibility with the measurements to tell that these are the most likely to occur. So this is again the process, sample the distribution, compute the evolution with the model, and update. So we have some specificities in this present algorithm. So in this present algorithm, we use machine learning for the forecast. So the process of computing the evolution of the system using a partial differential equation is too slow when you have lots of ensembles. So you cannot use that. So we use actually a machine learning representation of the PDE, and that actually is gaining traction. There are lots of papers now that work with deep learning algorithms to approximate solutions to partial differential equations. So we use that. Then we have a very fast representation of the forecast for a particular initial state. In fact, with the examples that we did, we had almost 1,000 times faster than the PDE solution, with a comparable degree of accuracy. Of course, the accuracy is not exactly is not as precise as a PDE, but it's very similar. And then the analysis process comes from the Kalman filter. So now what are the difficulties that we are facing? So the first issue is to determine what is the prior. So when you start to deploy your UAVs, what are the initial conditions of the problem? That's something that is very complicated. There are also other difficulties in terms of the prior, which correspond to the actual state, the actual model parameters. So when you use the flood propagation models, and these models, they have a certain uncertainty. So they, for example, they have many coefficients and other coefficients, and you don't know them in advance. The second thing is to optimize the sensor placement. So how to place your sensors that are either fixed or mobile. If the sensors are mobile, how to optimize the path of these sensors to maximize the information gain. So that can be done through several optimized information gain metrics. For example, you can use matrix that depend on the log determinant of the covariance matrix of the prime, or you have some other divergence functions that tell you the information gain for each measurement that you're getting. And then you have to quantify the uncertainty initially and quantify the uncertainty over time. That's something that is very complex because you start with a certain covariance matrix that is a wild guess, and you have to, as quickly as possible, converge with an accurate covariance matrix to give precise information to the responders. You don't want people to trust every point of your map with the same level of confidence, given that you have a certain covariance that will tell you that some of the points of the maps are actually a very low confidence. And finally, reconcile sensor faults. So these are things that we are working on these days with my students. So the path planning algorithm, to give a very brief overview, this is how it works. And we have a search tree, and we have some heuristics to incorporate partial information instead of running a full assimilation step. So technically, when we do the path planning, we should start with a specific point. We should then have a prior. We should then optimize over time over all the possible motions and all the possible tracks of the UAV, the information gain at the end. And select, of course, the tracks and the things that maximize the information gain, or the metric that we are using for information gain at the end of the time horizon. The issue with that is that technically you have to perform an assimilation step at each virtual measurement that you are gathering. So that very quickly becomes intractable computationally, because technically when you are going over some area, you're getting some measurements, and that measurement gives you some information. But when you are running the optimization program, you don't know what measurement you're going to get, obviously, because that's the surprise that will come in the future. You still have to optimize over the possible measurements that you are likely to get. And this is extremely complex because you have to run, of course, an assimilation step based on these virtual measurements, and that is too slow. So we have found a very good approximation by doing this heuristic information gain. And we could run with several time steps ahead the optimal path. And here you can see for this example in Austin, what are the optimal path for a specific scenario. So we also found that you gain some information. These algorithms have value. So this is shown by this image, because if you run randomly, so this yellow envelope corresponds to the extent of the information of the uncertainty that you will get when you randomly put your UAVs. So you see you have a lot of possibilities between this lower yellow and this upper yellow envelope. If you use these algorithms that we have worked on, the myopic algorithm is the one that works one step ahead. The non-myopic works multiple steps ahead. You can see that we have some very good information, and we are very close to the lower bound, to the best when you try random trajectories, the best trajectories that would maximize information. Okay, and so next is a future direction. So here we are interested to continue working on these. So what can be done next? Use synthetic aperture radar. So NASA has been giving a challenge in 2021 to use synthetic aperture radars to maximize information and to try to get maps of floods. We haven't participated to this, but I think that's going to be interesting to see to what extent we can use SAR to try to determine the extent of the flood. It's still an open challenge. Using fixed sensors, so try to monitor, of course, different things, and try to integrate all this information together between all the information we have access to with the model. With mobile sensors, we don't have the practical capability yet, but we are working on all fronts to try to improve these capabilities and see what can be done in the future. So that concludes my presentation for today. If you have any question, let me know about the presentation. Thanks.
I'll take a quick stab before I leave. This is a very interesting conversation. Chris, my name is Dev Niyogi. I'm one of your colleagues in your department. We haven't had a chance to meet yet, though.
Okay.
This is something we have been doing from the atmospheric end of things with the WRF modeling and using Cygnus and other satellite data sets. So, and with Jungfeng and others, we have been talking about how do we scale it down to the urban area. So we have some urban models in which we are trying to create the precursor conditions using downscale analysis. And so using the UAVs to sort of, or even your sensor data to either do the cross-validation or even integration would be of tremendous interest, not just from the flooding aspect, but also from maybe visibility and other aspects going forward. So would love to have a conversation going forward.
Okay.
And maybe Jungfeng and Vijay can follow up more on this as I get off to another call, unfortunately. But thank you so much. This was great.
Yeah. Thanks. Thanks. Yeah. That's it.
Yeah, thanks. I think this is really an interesting talk. So I wonder if there's some more question from the audience. I have one quick question. So in one of your slides, you show there's a link between the two UAV, like UAV1 and UAV2. Does that mean it's possible like to have the communication between the different sensors at the same time as well?
That's right. Yeah, our idea is to try to have the communication between the UAVs so that we can exchange information for the path planning. So we have worked with Kun, my student, on the distributed version of the algorithm to try to see what happens if we lose communication between the main station and the UAVs, to try to see how can UAVs talk together based on their measurements and the models and the crude model that would be run on the UAV, to try to see if they could continue working to maximize the information gain as well. In some way. Yeah.
Yeah, I find that aspect is actually quite interesting because in terms of the area coverage, it's actually a problem. Remind me, like I do a little bit on the distributed computing, and so where we want to coordinate multiple nodes to access the data, we have a similar problem. We want to avoid them to accessing the same data at the same time because that's going to be block the performance. So there's a kind of the protocol an algorithm in place and trying to avoid that collision of the resources there. But I feel like something might be similar here is in order to optimize or maximizing the coverage of the over the spatial area too. So
yeah, the main result that we found is that there is a suboptimal path that gives you a guarantee of suboptimality. Like you have a certain percentage that an upper bound on the percentage of suboptimality lost if you follow a certain algorithm. That was the main result that we have worked on.
Yeah, that's interesting.
Christine, this is a very nice talk and very informative. I have a quick question. So for this UAV, are this just look like this is like a larger predator, like a
they put that as an example, but yeah, for the actual missions, I think we should have UAVs that are, I mean, not necessarily as big as the Predator. Of course, the Predator is gigantic, but like this UAV that we have used back in Saudi Arabia, I think it was weighing maybe 10-15 kilos with a gas engine. And these UAVs, they can stay aloft for hours. They can really stay for 10 hours easily, and they will still have fuel in the tanks. The problem is that you cannot fly these things over cities. I mean, that would be insane because they would have 100% chance of crashing in a city somewhere. If you have the current algorithms for autopilots of UAVs, they are very simple, very crude, and they would stall at the first, for example, high draft. And in these flood events, you have huge downdrafts, updrafts, and people fly UAVs in good weather conditions. Usually, they never fly UAVs. I mean, if you have too much turbulence, people won't fly UAVs because they are too difficult.
Yeah, it's very related to this question. We are trying to get into the UAV area. We realize there's no fly zone almost everywhere within the urban boundary. So right. I see you have a map of Austin. How did you do that?
So we did that in Austin. This flight here, we did that a few years ago before it was
no fly zone.
Yeah, no fly zone, exactly. So we did that. So what was it? It was here. Yeah. So that was at Austin Radio Control Associates. So you can fly UAVs. You can fly UAV. I mean, you can fly basically remote control airplanes. That's technically a UAV as well in these locations. But that was at that point for research. It was still allowed to use UAVs. It was clarified only a few years later that we couldn't fly any UAVs. So now these UAVs sit in my lab. We cannot work on them anymore. team up with UAV companies or things to try to see if we can use them. Because in that case, I wouldn't need to do anything, any flights. There is still a possibility of using contractors to fly UAVs, but you cannot fly them anymore.
Just sorry to follow up on this, because most casualty during the flood happen in an urban area, like people drown during the underpass. So if you cannot use this in an urban area, that's sorry,
that's a big...
like you know where I'm going, right?
Yeah, of course. No, we cannot use them over urban areas. I would say now I think it's too insane. It would be insane to use them over areas. But I think there is definitely a lot of room for progress, because it's the same as, technically it's still a control problem. I'm pretty sure that we can make UAV platforms that are optimized. Right now, the UAV platforms are optimized to minimize drag, to maximize loiter time, and they are meant to work on good weather conditions. Nobody has worked on UAV platforms that are specifically meant to work on bad weather conditions. But I definitely think that there is a lot of potential. You can make UAV designs that would be much more maneuverable. For example, the airplanes that are used, like aerobatics airplanes, for example, they have a huge maneuverability. They don't have good performance, but they are extremely good at reacting to terrible turbulence, and they are very sturdy. So we could make UAVs like that with some autopilots that would be smarter. Of course, you would need more inputs. You would maybe need to do some airflow inversion to estimate what's the airflow in real time around the UAV. At that point, that plus maybe some ballistic parachute in case everything goes wrong. You can always put ballistic parachutes that open on UAVs. At that point, I think it would be the trade-off between the risk of flying the UAV and the risk of casualties would be in favor of flying the UAV over a city at that point. But right now, given that it's a guaranteed crash, I think nobody, given that these UAVs, they cost, for example, these kind of UAVs, they cost tens of thousands of dollars. I mean, nobody would risk their thing flying something like that in bad weather, for sure.
This is very interesting. I might reach out to you
Sure.
for future work. This is very nice.
So good. Thanks.
And also, I saw the emergency services will be exempt from the no-fly restriction, right? So the fire department can fly their drones over the scene of the emergency as well. So I imagine, like, if we have the algorithm working, we do be able to contact a city and have them adopted.
Right, and also the FAA is now less conservative than it used to be on drones, because they see that now there will be more and more drone applications, as well as also maybe urban mobility as well, and all these things. So there might be some exemptions, and now you can find easily transponders that can fit on drones that can also be used around airplanes as well, so that even if you're in an area that is, the airplanes can basically have their anti-collision devices recognize the drone and commercial airplanes, so that it would reduce the risk a lot as well.
I see another application of your sensor and your plane. This is not only for flood, you can also detect and predict other natural events like a wildfire.
So we were also interested a lot in tornadoes, but tornadoes that's a bit more extreme, that definitely no UAV can fly in a tornado. But if we can make something sturdy enough to fly in terrible weather, tornadoes would be also an interesting possibility, because if you are able to fly a radar inside the UAV within a zone that is close to a tornado, usually the problem of tornadoes is that the weather radars, they have a certain resolution, and usually the distance of the tornado to the radar is quite long. It's a few tens of kilometers. So at that point, it's very hard to detect rotation motion, for example, the mesocyclone forming and all this. I mean, you can still detect it, but it's very subject to interpretation. If you could fly in, whenever you have a very strong front, if you could fly a few UAVs there and use the information from their radars in real time, you could definitely detect very quickly the mesocyclones when they form. You could have a much faster warning, for the tornado forming and the touchdown and all this. So that would of course not save anything, and the tornado would still form, but it could still give precious minutes or to people that are around to take shelter. Or that's. But fires as well as are possibilities, wildfires and all these. Anything that is following a partial differential equation.
Okay. Yeah, it's really interesting talk. So it's already 15 past 30.
Sure. Yep.
So I do want to close the presentation and talk for today, but Junhua and I might want to follow up with you maybe as well as Dave and to follow up with you separately on this.
Okay.
Thank you very much for your time to give the talk, and thanks for everyone stay so late past the time. So I do want to point out we have the website smartcity.tech.utech.edu, so you can join our mailing list and you can watch for our past talks and recordings as well as for our upcoming talks. Thank you very much. Bye.
Thanks. Bye.